Hello, everyone. Thank you for coming to this talk. Already been introduced. I'll skip to the next slide happily. Nearmap is a provider of high-resolution aerial imagery and location content. We are headquartered in Sydney, Australia, as mentioned. We currently capture urban areas of United States, Australia, New Zealand, and Canada. We specialize in capturing frequently and providing crisp and current images. Now, recently, we hopped on to AI bandwagon, and our experience has been nothing but phenomenal. Our AI team has been doing lots of exciting work, building derived content on top of our imagery. Some of these are building outlines and things and stuff detection, things like swimming pool, power pole, solar panel, and stuff like vegetation, roads. Now, this isn't just R&D machine learning. We are talking about petabyte scale machine learning or AI. In fact, we have been churning through petabytes of aerial imagery, generating semantic content of every ground we have covered in a very short time. To put figures to that, we're talking about burning 2,000 GPUs for 2 weeks to generate semantic content over 1 million kilometer square area at a resolution of 5 centimeter per pixel in that small time. And that's utilizing only preemptible instances because obviously we want cost to be low. And all this has been realized only because of Kubernetes, because of the abstraction that this platform provides and simplifies the operations, that we have been able to realize that sort of scale with our AI workload. Now, AI isn't just about model. It requires equal contribution from a lot of skill sets. It's not just about data scientists. It's also about engineering, DevOps, and data ops. And that's why Kubernetes has been our choice of platform. Now, I wanted to show you how San Diego looks like from the lens of our machines. This is San Diego in green and red, green for roads and red for roofs. And it looks pretty beautiful, I must say. I would love to talk about all these, but today we are gathered here for much more important, and I say urgent issue, which is reproducibility in machine learning. But we are going to be talking about how we are running our inference pipeline on Kubernetes in Sydney Forum. So if any of you are coming down in Down Under, please come and say hello. So which brings us to really today's agenda. I'll be talking about briefly what machine learning is, why reproducibility matters, and what are the challenges in really realizing machine learning. How much reproducibility then do we really need? And what are the tools and techniques that we have at our disposal to really write a reproducible machine learning code and infrastructure? And then let's have a look at how to do that on Kubernetes. And there is an extension to reproducibility, that is replicability, and that is being robust to certain noises in the model. How do we do that? And then I'll open the floor for question. So very broadly speaking, machine learning is all about running complex mathematics over top of your data to find patterns and associate meaning to those patterns. And when we think about machine learning, we really think about that sort of workflow. We have the data, we transform it to get it trained ready, then we train it, tune it, and we probably improvise it for boundary conditions and adversarials, and then we calibrate the model and evaluate the model. And if you're happy with it, that's where we think the model really ends. But in reality, the workflow is much more complex and sort of looks like this. The buck doesn't stop at obtaining the model. We have to have a release process in place. We have to make the model available for consumption. And often, the output from the model isn't quite usable by the end user. You have to really transform it to make it consumable. So that's post-processing and the augmentation, the bit that happens at the end, and it's probably where your customer's interest lies. And then we also have a funnel that goes back into your data set to continuously keep updating your model to improve it for wherever it's not performing very well. It's also commonly known as adaptive sampling. So this is the workflow that, in my view, is really the reality. And for the rest of the session, we will be sticking to this kind of workflow. Now let's take a pause and talk about why reproducibility really matters. So reproducibility helps with understanding, explaining, and debugging. And it's especially hard in machine learning when just your output may change just by shuffling your data. So your data is still the same, but you shuffle it, and you may end up getting the different results. And that's why reproducibility is hard in machine learning. It's all the more hard because we have deep learning, which are also tagged as deep nets. We spent 10 years of research really trying to understand what these networks learn, starting from visualizing the higher layer features to interaction between neurons and also building activation atlases, but still not quite sure what the model does and why it makes some inferences that it does. And in that circumstances, given the main brain that we don't understand, we really have to understand what's input and what's output, and having that assurance that we'll get to the same result becomes an important factor. And it's not just for us for understanding and debugging. Our customer also expects the answers to be verifiable, reliable, ethical, and unbiased. Making your answers reproducible makes them credible, as Leakin has said. And correctness is important too in our answers. These are examples of some of the great AI failures of our time: tagging humans as gorilla, giving wrong cancer treatments, recommendation for cancer treatments, or having gender biases, because things go wrong, and they often does. And when that happens, understanding debugging and correcting the course is really what helps. So again, reproducibility does matter. Extending out and building upon is only possible when the preceding layer is stable and reproducible. And that's, again, another reason why reproducibility is important. Now, I can go on and talk about why reproducibility is really important, but I think let's pause here and talk about what are the challenges in realizing reproducibility in machine learning. I divide the challenges into 5 different dimensions coming from hardware, software, algorithmic, process and practice, and data. Let's look at each of them individually. So machine learning computations nowadays requires gigabyte or terabyte floating point operations, which are really complex and require specialized hardware to perform that sort of computation. But it's a common knowledge that due to asynchronous computations on the GPU, different GPU architecture gives us different results. So if you have your data and same algorithm, if you run it, you may end up getting different result if you run it on K80 or different GPU. And it's a lesser known fact that even running computations on CPU with parallelism may give you different results. And there's an interesting presentation by Corden talking about why my application doesn't give the same answer that I recommend watching if you're interested in this segment. And it's not just hardware. Libraries performing intensive computations sometimes do not guarantee same bitwise result even when run on the same GPU. And this is an excerpt from CUD and NVIDIA's CUDA deep learning library that do not guarantee reproducibility on some of their routines. And it's not just CUD, and even TensorFlow routines, some of the routines like backward pass do not guarantee reproducibility when run on GPU or even with parallelism. Now again, there's a great presentation by Duncan, who has done a lot of work with determinism on machine learning with TensorFlow that I recommend watching. And it's not just computation-intensive workload. Sometimes even much simpler deterministic workload may give you different answers. Why? Well, because it's software. Now, this is a true story that we went through. We released nothing but a version change of a PyProj, which is a geospatial library, and upgraded just that particular library from 196 to 240. And suddenly, our location calculation for San Diego Convention Center were somewhere out in Miramar off Gold Coast. Imagine giving that results to customer, or even ordering your pizza and enjoying your dinner. So, and machine learning really loves randomness. If we don't have a solution to a problem, we try and randomize it and hope it will sort out itself. We have randomization coming from algorithm like dropout, random initialization, and we also have randomization coming from process and practice like augmentation, flipping the images or rotating them, or introducing noise to make the models more robust, or simply just shuffling your data to remove the bias in the data. But look at how many seeds I have to set up, and these are just the global random seed. I'm not even talking about the seed that goes into the algorithms or your layers. And then we have data. This is the beast of all the challenges that we're talking about. When we're talking about machine learning, we are really talking about large data set. And when the data is really large, we're talking about all sorts of problem related to data poisoning, overrepresentation, underrepresentation. And as Scully has said, no input is ever really independent, and same applies to data as well. No data point can be seen in isolation. It really has a correlation with the rest of the data set. So, and here's a great example of Tay, Microsoft's chatbot that came to light, trained on trained to be a superhuman friendly, and it started off being really friendly, and we human polluted him and it became super noisy in less than 24 hours, and then it never really saw the light of the day as we knew him when it came to inception. So that's a good example of why reproducibility really matters and where the challenges are coming from. And as if we didn't have enough problem and enough challenges making us not realize reproducibility in machine learning, we have concept drift. Our concept of things and stuff keeps evolving as we go over time. There's the first prototype car as we envisioned it, and now how we envision a car when we think about, really what a car looks like. So it's not just about getting to the same answer on your same model, on your same iteration, but now we are talking about continuously generating more and more models over improved data set, and also having the reproducibility across everything. So it's not just reproducibility, but we need full automation and governance across everything. Which brings us to how much reproducibility do we really need? There is a middle ground to this. If we can say that as long as we can explain our answers, understand, and reclaim them, and have a roadmap to reaching to the same conclusion, then we may be okay. Today, it's possible to write 100% reproducible code, but it comes at a cost of speed, which may not always be at our disposal. So having right process in place and doing the best we can is a way to realize 100% reproducibility. And we'll look over these in a little bit more detail shortly. So this is how to realize reproducibility again. If we can write reproducible ML code as much as we can and version control everything, then we can have reproducibility and also explain the variances that we are seeing in the answer and debug them and have more control over it rather than just shrug and say, I don't know how I got that. Probably one of those reasons why I didn't get the same answer. Not something we would like to go to customers saying. So what I have is a simple example done on an Oxford pet set data set. It's a very simple semantic segmentation model that segments image pixels into 3 categories, foreground, background, and unknown. And I've taken that example and transformed it into an end-to-end ML pipeline on Kubernetes. For the rest of the talk, I would be referencing code snippets and files from this repository. So talking about the first step, which is writing reproducible ML code, it's really very simple. We got to have version control on our code, which I believe 100% of us do that. If not, please do. And then reproducible runtime, think PyProj. It happens a lot to us as well. If you don't have the libraries pinned to the same version, it does cause some unexpected behaviors. And then randomness, please do seed your random layers, and you can change them when you do need. Then rounding, overflow, precision, these kind of problems we need to be aware of. There's other bucket where we're talking about dependency issues coming from libraries. Like how I mentioned before, backward pass is not guaranteed to be deterministic on GPU when run on TensorFlow. And there are many different issues that sits in TensorFlow bucket that sort of makes your code non-reproducible. Now, there's a way to make it reproducible, but I guess the choice is yours because it comes at a cost of speed. But everything that can be achieved, things like pinning library randomness, that is something that I would recommend doing to realize reproducible machine learning. Now how do we do 100% reproducible machine learning code? This is an example for that. So train.py is a code that I have in that project. I really have a standard UNet-based network with a VGG or MobileNet 2 backbone, if you are familiar with deep learning. And it's a very simple example, but all I have is I have all randomness seeded. I have all libraries pinned. And then I have global seed set defined by set seed that's shown on the screen. And on top of that, I have this routine that I call set global determinism that sets all the deterministic flags of libraries that I'm using in my stack, and that guarantees that all my routines are deterministic. And then I also have the CPU parallelism flags turned to 1, and then I patch TensorFlow for determinism. This goes back to the backward pass example that I gave. Now, doing that on top of my code guarantees that every single time I run my code over the same data set, I get 100% reproducibility over it. Now, if you wonder what happens if I forget to set a seed or if I don't write reproducible code, then have a look at this. I have results from 2 models, one trained with 100% reproducible code, and the second one is trained with almost same code as one, but just one drop layer unseeded. Now that's just me forgetting one seed, and you can see the difference. The first example is really simple example, and you can see only subtle difference on the color of the dog. But look at the second one. That's a complex example for a unit model, which is very simple, and you can see the difference on the shadow in the prediction. And the third one, that's really hard. Even I can't tell if it's a cat or a dog or which animal that is. Really looks camel to me. But anyhow, look at the results. We are talking about significant difference in the predictions, and that's just one seed. Everything else, including flags and everything, turned on. So we talked about writing reproducible ML code. Now let's talk about version control and full provenance. First up, what to version control? The way to realize machine learning, really basically AI system is comprised of your infrastructure and your platform orchestration layer, which is Kubernetes in this context. And then we have lots of libraries or software that sits on top of it, like things like Cubeflow, Pachyderm, Seldon, Argo, and Istio. This is what this example is using to demonstrate how to realize end-to-end reproducible machine learning. And then I also have source code on top with the dependency and the container and data on the other side. And the process and practice sort of ties everything together to realize the end-to-end reproducibility. And the challenges are tagged alongside of each of the layer. On which layer, what challenges do you see more often? So first up, let's look at versioning environment. GitOps is a very popular concept now in cloud native and Kubernetes community. We basically provision our infrastructure from a Git resource. So every change onto your infrastructure is version controlled and is really driven off your Git repository. And this is what this example is using. Basically, what I'm advocating for is everything should be version controlled, and this is not just your code and your stack runtime, but also your infrastructure. And the example app, really all you need to do is bring your own Kubernetes cluster, install Argo CD, and then just install these Argo app, which are defined already in the cluster. And this provisions your cluster for all sorts of Kubeflow 6.2.0 and Pachyderm 198. And on the back of it, you get lots of training frameworks like TFJob, PyTorch, Pachyderm, Kubeflow, Argo, Katib, Seldon, TF-Serve, and many other serving frameworks, and also Istio for serving, excuse me. And then let's talk about versioning everything else. What's everything is really the process, the workflows, that whole pipeline structure, and the data. So just reminding you back again, this is the workflow that we are working towards, and each of the steps in this pipeline is the workflow, and the data that it generates, the artifacts that it generates are all the data, including the data that you feed to your model for training. So if I take that pipeline and rejig from the artifacts perspective, I'm looking at this. And to explain more on what that is, I have this stream pipeline, which is a continuous funnel that keeps dropping data into my warehouse. And on my warehouse side, what I'm doing is really segmenting the animals' images and masks indexed by their ID. And then I do the transformation on my data. Basically, I'm slicing or partitioning my data into 4 different buckets, which is training, validation, calibration, and test, and put each of the individual pet that falls into that bucket in that particular repository. And after that, I perform tuning, and I expect the tuning to consume training and validation set and give me the output as an optimized hyperparameter that I should be using on that particular data set and the algorithm that I'm using for training. And then I effectively train the model in the model pipeline, which is in the center with the optimized parameter, and that gives me the model that I'm happy with. And then I do the calibration on my predicted models to really present my predictions as a confidence. And that gives me the calibration weights, and then I perform the evaluation, which gives me the reports of the model, so how good or bad our model did overall for all the metrics, and how it performs on the boundary conditions, and deduplicates my files and gives me the model and model file and actually the weight file, and also a summary of the results. And on the back of the evaluation outcomes, I probably perform some sort of release operation looking at the metrics of the model and also looking at testing the model against some of the boundary conditions. And if I'm happy with that and I want that model to go into production, then I start the release, which is a serving component that starts up serving. And then there's two APIs really. One is that's serving the prediction over gRCP or REST, and also one endpoint that's a feedback endpoint that consumes the true prediction that should be, and also the prediction that's model has produced, and that feedback is then fed back to the data warehouse, which obviously you probably would want to put a verification step there because it can be exploited to a great extent if exposed. So that's why I have the manual verification there. But the point here is that there needs to be a funnel that goes back into your warehouse, taking in all the corrections that should be in the model. And so with that diagram and with that sort of flow of the data and the artifacts, let's talk about what are the tools we are using to realize that solution. Now, we're using Pachyderm for provenance. Pachyderm is a great tool for data provenance. It gives us a Git-like construct for data. Basically, your data sits in your repository and everything is versioned on yours, so you can pretty much ask for your files on a particular version, and it deduplicates under the hood. And then there is another version of automated repository where your pipeline really acts on your input. So any input repository with a particular version, it will act on the input data and creates an output and stores the output in the repository with that version. So then we can use these two constructs to build a complex diag, something like what we looked before, and have a full provenance across everything. So in our example, Pachyderm is going to be doing the heavy lifting of provenance. And then we obviously have Kubeflow. There are quite a few talks around in this conference around Kubeflow and KF serving as well that really tells us the adaptation of this tool. So I assume that I probably don't need to talk too much about it, but Kubeflow is really it's not a solution to a machine learning problem. It's just bringing all the solutions together into one platform to solve machine learning problems. And we're really talking about tuning, training, pipelining, and Jupyter, because of course no data science is ever possible without a notebook. So then we have Kubeflow that we would be using to perform ML-specific operations. But we have a problem because Pachyderm and Kubeflow don't gel very well. Kubeflow is very Kubernetes native. Pachyderm, though runs on Kubernetes, it's not very native to Kubernetes. You can't really use operators and have a better integration between Kubeflow. You can't really use operators. The teams, I'm sure, are working on it, but as of today, it's not possible, and that's the challenge we have in seamless integration. And we are going to have a look at how to really simplify that to some extent. So I'm taking tuning as an example here, and this is a specification of Pachyderm. You really specify your input, and in this case, the transform is the repository that we looked at. Now I'm going to slide back to show you what transformation was, which is the third repository there, and it's creating the training, validation, calibration, and test set. So when we are tuning, we really want the training and validation, so we really want the input coming from the transformation step. So then in pipeline, we are saying from transform, give me everything, and then apply this transformation, which is do the tuning for me and generate all the results into my tuned repository. Now this works great, wonderful. I use Ray in container, and it does the hyperparameter tuning using a really complex algorithm called hyperband. So the point here is that complex machine learning is possible in Pachyderm, but because it's not leveraging the benefit of the distribution and scale that Kubeflow provides, we're sort of locked down on that container, and we'll have to wait for a longer time to get to the answer. But then we can use Pachyderm in conjunction with Cubeflow, and that's the other bit that I was talking about earlier. So this is an example of the similar tuning sort of operation, but what we are doing is we are taking in transform repository as an input, and then we are applying the transformation step, which is tune with Katib. And what that does is starts up a Katib experiment from Pachyderm container and injects the provenance information. So what sort of version of tune repository I should be using, and what should my output version be? And with that, it starts the trial, and trial then has a Pachyderm client sitting within itself that downloads the files from Pachyderm with the repository name and the version. And once it has downloaded all the files, it starts the execution and completes the trials, storing the outputs in the Katib repository for that particular trial. At the end of the experiment, all the trial results are then collated, and then that's available into the experiment. And the pipeline then extracts all the final results of tuned parameters and stores that into the data pipeline with the provenance against it. So that's Pachyderm in conjunction with Cubeflow with full provenance, and that's an example of how we cut from Pachyderm to Cubeflow and come back in. Here's another example of serving the prediction with the version generated by Pachyderm. So we're doing pretty much same thing. We start up a Seldon deployment from Pachyderm pod, injects the provenance, and once we inject the provenance, the Seldon deployment then takes care of starting the pod with the model in it. And when the pod starts up, it really uses the client to download the model file and the calibration file that we looked at. So I'm going to slide back again and show you what the model file we're talking about. So this is here, we're talking about model.h5 and calibration weights. Sorry, which in case of Seldon pod, it will download the files and start making the prediction API available onto that particular version. And then the API is just available with both feedback and serving. Now, I'm being cheeky here. I've hacked up the reinforced learning API of send feedback to do the feedback, but it's certainly possible to add a custom API on top of Seldon deployments. And this works with any other deployments as well. So now talking about the replicability, which is an extension to reproducibility. And this caters to the scenario where we are not just talking about getting to the same answer on your same data, same algorithm, but also what happens when your input is slightly changed or slightly perturbed or maybe added a noise. And that's when we start talking about robustness. There are quite a few approaches around to make your model more robust. Things like Clever Hands, which is Leakin's library along with some of his colleagues, where you improve your model with, just like augmentation, you sort of improve your model with introducing noise on the input set. There are similar libraries like Google's NSL, Natural Structural Languages, I think it's called, their Foolbox, and there are many more libraries that allows you to robust your model. And these are, there are some great sayings by saying that model generalized across architecture and training sets are the good model, and it's really required in our time where our answers are really impacting, end users. Think about loan sort of scenario, or even in the image, like if, for example, I talked about going back to the example of pet set here. So if I'm doing an inference on looking for poles in the imagery, and that's really just a very small artifact in a big imagery, and it's really hard to miss. If just losing out one dropout layer gives me that sort of result with so much of variance, it's really easy to miss out poles, for example. And it's really important to be confident, reliable, and reproducible in our answers when we are going out to customer and impacting really their workflow and simplifying their lives. So now this brings me to what are the other tools. So I know about DVC and MLflow that can be used to sort of realize MLflow, but I learned in this conference that there is another way to do that, which is now using Aricto with Cubeflow. I think it was something new that I didn't know before, so that's another way to really realize that. And that's really all. If there's any question, I would like to take that.